So, welcome everyone to CSCS for 3 days of fun and games with multi-core processors on some of the machines that we've got. So, I'm going to be taking you through the beginning of, I think, every day, and then there's a number of other people in the room who will be teaching other aspects of the course. So, what have we got for the next few days? So, we want this to be quite a flexible program. It depends on what people are actually learning, what they think they might need more time with. And we said, please bring your own code and let's play around with some of the tools with your codes if you have them. So I'm just going to do a brief introduction, looking at some standard multi-core architectures this morning. Then very brief introduction to some aspects of single core cache and TLB. What are these things? And then we'll move on to vectorization. And then we'll be looking and using a couple of compilers, 2 or 3 compilers, to see what you can get out of vectorization. See the speed-ups that you can expect, just on very, very simple little examples. And then Ben Cumming is going to then move forward with that vectorization with a few more complicated examples. And then at the end of today, we will have a couple of examples from Ben and Gilles Forestier on cache efficiency, on vectorization, and going a little bit more into depth with a standard example that we like to use everywhere, matrix multiplication, but it's something where you can see the power of the techniques. Then tomorrow we get into multi-threading. So very quick primer, because you should all know OpenMP to some degree, because that was written down as a prerequisite, but we will just make sure that you remember what you need to remember, because there's only a few things that we're really interested in for what follows, and that is an example of a multi-threaded tool. A tool to help you actually put those directives in, know where to do the scoping and so on. Now, we're using one that's on our Cray systems here. There are 2 that we've been playing around with. The other one may be to some of you more useful if you don't have access to our Cray systems. From Intel, but we're just showing this one because it's the one we've just got a little bit more experience with. They're very similar tools. We'll also look at a couple of other tools, then looking at a parallel debugger, something else you might find very powerful in helping you with your threading, and some common threading bugs. I know we've got, again, time for quite a few in-depth examples that we've prepared. And these are the sessions in particular where you might be wanting to use your own code if you've bought one. And then on day 3, we continue with multi-threading, because although there's 2 strands to what we want to talk about, one is vectorization and one is multi-threading, because these are both required if you want to get the most powerful usage of modern multi-core processors. Threading is the one where you have to do more work generally. So we'll be looking at some issues, some cache coherency and cache thrashing issues that can slow your codes down, affinity and NUMA issues. Looking also, you'll be able to see the difference between AMD and Intel processors. Briefly, just to touch on people who have got MPI codes, and I know there are a lot of people in the room who do have MPI codes, and how MPI and OpenMP need to be used together. And then we're going to also have a brief look at the Intel Xeon Phi. We were hopeful that we would have our Intel Xeon Phi cluster up and ready, but unfortunately we were really talking about 2 or 3 days in whether we could get it, and I think the parts didn't arrive in time, did they? No. So unfortunately we can't actually get you on the machine and accessing, so instead it just has to be a session showing you what this is about and how this takes to an extra dimension in some ways, the vectorization and threading that we're talking about here. So you've got the course logging and slide tutorial, sheets. So I'd like you at about this stage to just make sure you can log in using that sheet. Okay, we'd rather get any problems that we're going to get for logins out of the way at the beginning of the course, rather than when we get into it. I'll just keep talking, but if you can open your laptops, get onto the wireless, and then try and get onto the machine, Ayla, and then from there another one. And I've picked a random one, and this one's called Toady, just to make sure, because then it gives us an hour and a half to solve any problems before we get into the real practicals that we want to do. There's a common place that we're putting the slides and tutorials, and that is when you've got onto one of those machines, Ayla or Toady, there's this directory. But we'll repeat this when we actually come around to requiring you to get hold of the tutorial material. You'll need to then copy any slides over onto your local machine. There is events available, or Evans, or however, because there's some French people taught me it, so it may have a strange pronunciation, available on Ayla, so you don't necessarily need to copy them over, but it's probably obviously easier for you if you do. One logistic thing I forgot to mention. As you came in the door, you will have noticed that there's a little bit of reconstruction going on, so we don't have a reception at the moment. So if you want to go out for something, perhaps for a cigarette or whatever else it may be, come and just grab this guest access pass that will allow you to swipe back into the building when you've finished. Particularly as it's a bit of a cold day, so you might not want to be stuck outside for too long. So I'll carry on talking as people are getting in, and just because I can see what I'm going to say on the next slide. The next slide is simply just one to say, just like to have an idea of who we are, who's actually here. So could people put their hands up if they're Fortran programmers primarily? Okay. And how many are C, C++? Okay. It's changing each time, yes, exactly. The battle goes on. This battle may be lost for the Fortran, but the war, well, anyway. So, just to confirm, so everyone here understood the point we made about you do know some OpenMP. You're familiar with OpenMP. Anybody here who's come and they don't really know anything? Okay, maybe the primer will give you enough to be able to get going. We pick OpenMP as a threading model, not because we say that it's better or anything, but simply because it's everywhere. And as you saw, C and Fortran can both take advantage of it, whereas a lot of the other threading models are particularly specific to C++ in particular, has most opportunities. Just out of interest, how many people have brought a code with them that they want to work with in any of the practicals? Okay, good, right? Hopefully you'll get a little bit more out of it then by having your own code. And particularly when we see some of the tools in the next, particularly beginning tomorrow. And there's a number of people here who aren't CSCS users. So how many people do not have access to Cray machines or CSCS machines? Okay, so it's maybe just 3 or 4 people then. Okay. As I said, it's not a course where we're required to be a CSCS user. I know there's some people in the audience, I can see one person who might be able to become a CSCS user. And that's why when we come to the parts of the course where we're using specifically Cray tools, we're saying this is an example of a tool that you can also get access to from, for example, Intel. So, has everybody tried to log on and succeeded? Yep. Anybody had a problem? Oh, okay. So, I don't know what your motivations are for wanting to learn more about multi-core, but hopefully they're similar ones to the ones that we've got. And so, our background motivation works along the following lines. This machine here was our brand new flagship machine in 2005, and so in 2006 it was still our flagship machine. So I'm quite legitimately able to say that 2006, there we go. This machine is a nice one, and that we'll arrange a little tour of the machine for anybody who's not been in there during the 3 days. And you'll be able to see this without the pretty mountain on the front, unfortunately. Just black cabinets and so on. But this is our brand new flagship machine. It's currently just going through memory and processor testing. All right, so we haven't even got access to it yet. It will really come into production next year. It's a new Cray CX30. This was only announced as a product last month. This is the largest one of these in the world at the moment. This is 12 cabinets, and the only other one is one in San Francisco that is, or Oakland in California, that is 4 cabinets, and this will be the largest for quite some time. But it has arrived in 2012, so I can say this is 6 years difference. Okay. What we see is that our flagship machine had a peak performance of 5.7 teraflops back in 2006. This new machine is 750 teraflops. So you can see the scale, the difference in computational power. These mentioned down here are double precision peak performance numbers. Now, the number of compute nodes, yes, we bought more of them. We've probably spent about twice as much money on the machine. So that's where some of that power goes. But the rest of it, all of that is sitting down in watts on a node, 64x performance. So when we had this machine arrive as a high-performance computing center, we wanted to see what people could actually make out of this, and could they actually use this in some way at scale. And in those days, if we could get somebody out of 1,100 nodes running 128 nodes or so, that was pretty reasonable for us. That was pretty good. 64, 128, 256, that's what we were actually getting at the time from people when they got on this machine, and particularly in 2006. They were using a reasonable amount of the machine. Over here, this one we haven't turned on yet, but our other one, Monte Rosa, that we sit at the moment, people haven't, in many cases, been able to actually move on very much. So there's a lot of very, very, very small jobs sitting around and some medium ones, and not many people are actually able to really use the full machine. We need to be able to get much better performance, much better scalability out of each one of those compute nodes if people are going to be able to use this effectively for really grand scale scientific experiments. And so that's our motivation for doing this. This 64x, where does it come from? One of the easy ways of seeing where that comes from is that there are 2 multi-core processors instead of 1. Okay, so I've got 32x to come out with. This has 8 cores. That one had 1 on each socket. So that's another factor of 8. Still got a factor of 4 missing. And that factor of 4 comes from our vectorization that we'll see later on, early this afternoon. So that's the beginning. Everyone's been able to log in. You saw, did you? I'll just put it back up. Everybody got the information about where the slides will be. So there are 4 sets of slides in the slides directory. That's the ones for this morning's session and so on. And they'll be put on as people prepare them, as people are about to give their courses. They're prepared, but as they're just finally tuned. Okay. So, on to the first topic of the day. Sorry, wrong topic of the day. And that is looking at the architecture of modern multi-core nodes. So we just have to understand something about the architecture. Most of what we understand about the architecture we'll learn as we actually come across the different topics. Oh, I've left a subtitle of presentation in there. So first of all, the question is, what architecture are we targeting? We're not targeting GPUs. We're not targeting historical architectures, modern multi-core. But we can just look at a very simple processor, and this one is actually not one that they're looking at, for the single core aspects of it. So this would be an AMD. So the first thing is we have the little piece, the instruction, decode, and execute. Not something that's particularly interesting for you, maybe, but this is This is actually where quite a lot of the power goes in one of these processors, and we're power obsessed now. Everybody in high-performance computing is completely power obsessed, because if we want to go to the next generation of machines, we can't continue to burn power as we did in the past. So instruction decode and execute takes quite a lot of power, getting these instructions down and finding in some way that you can actually get something going, floating point, integer, you name it. That's significant when we come to the vectorization, because one of the things that vectorization does is you only have to do one decode for quite a bit of data. So therefore, it's a bit more power efficient to be able to do vectorization. Then we have integer units, not what we're normally that concerned about in high-performance computing, because we're more concerned about the flops, but still quite significant. Then here we have the floating point units, and then some loads and stores and registers. Quite simple, single core aspect. When we come to multi-core, all we're doing is really, quite literally, just shoving these things together. The only thing that then we do is we start to divide up, maybe amortize some of the cost. So the caches, for example, may be reused. And we'll look at caches shortly. So just to let you know that already you're a parallel programmer if you program at all. You just don't realize it because you don't have any control over it. So this instruction level parallelism allows us to get more instructions going at the same time. And one of the reasons why some of the people who are now working for GPU manufacturers, Bill Daly, for example, has talked about, we've reached the limits of instruction level parallelism. We can't really do much more with that because we start to do all sorts of fancy things, out of order processing, keeping a lot of records that the processor can do, and it's all energy inefficient. So a modern server processor can issue multiple instructions if they're very different instructions at the same time. And this is something we call superscalar processor. So I like to use some analogies. So here, the analogy here would be something along these lines. It's the day after a party, everyone's woken up with a hangover. We need to actually clean things up. So somebody goes in, somebody's going to go in and do the washing up. So they're going to scrape the plate, wash, and then they're going to dry the plate. Okay, fine. But the person as well, if you didn't have any instruction level parallelism, somebody would have to go along and that same person would have to collect the plate from the dining table before taking it in, and then afterwards put it into a cupboard. Yes, it's nice and clean. If we use, the collection and the putting it away are separate events from the actual cleaning. So we can get other people involved, they can do those activities. That's superscalar, yeah? We've got a load activity, getting the plate from the table. We've got a store activity, that is putting it away, and we've got the processing activity, and that is the one of actually washing the plate. Now, another thing we get from modern server processors, we can do some things out of order if there's not actually a dependency here. Okay, so we can do multiple things at the same time. So sometimes your processor will be going along and it will see that it's got to issue a floating point instruction, but it hasn't actually been able to load the data yet. So it will not just stall, it will look what the next instructions are and see if they're actually dependent on anything that it's currently had to do. So if it finds instead that the next two instructions further along, there's an integer instruction which it does have the data for, and which it doesn't need the floating point unit for, it will try and get on with that instruction instead. This is another way of managing to keep the thing going. And then when that data is loaded, it will go back and do that floating point instruction. And modern processors might be able to do 40, 50, 60 instructions out of order. There's quite a big depth of how long they can keep going before they run out of the ability to find something useful to do. Now, going back to the washing up, said we've got these completely separate ideas. Somebody's loading things, somebody's putting things away, and somebody's doing the processing. But you know what it's like to wash up. There's actually, you don't just scrape a plate, wash it, dry it, and then keep going back in order. Actually, you can get two more people in the kitchen. One's going to scrape the plates, pass you the plate. One's going to then wash the plate, pass it to somebody to actually dry it. That set of different divisions of a single process, of a single activity, is what we can also take advantage of in our modern processes, and that's with pipelining. So this is like feeding new material into a factory pipeline. So rather than taking 3 cycles in our particular washing up case to get one piece of pottery washed, we can actually, it's going to take 3 cycles anyway, but we can then get 1 dish per second, per cycle coming out. The same sort of thing here we can do in floating point instructions. A floating point multiply is actually quite a complicated thing. It would take a few cycles on, or a multiply add, for example. A multiply add combined instruction on an AMD Interlagos processor takes 6 clock cycles. But if you pipeline it, you can keep feeding a new one in and get 1 out every operation. This is all parallel. So there are all 6 different stages of the pipeline are going at the same time rather than stalling. And so it's quite simple. Step 1 gives us the input. Step 2, step 3. It takes us several cycles, and then we can start on step number 6. We're starting to get our results. Now, if we've been able to keep the pipeline busy, the results will pop out 1 per cycle. So this is allied in some way to what we will look at with vectorisation later, where we have to get things together in blocks, and then we can issue a single instruction on multiple pieces of data. Here we're not issuing multiple pieces of data, but if the compiler is able to get your instructions in a way where it can see that it can keep issuing these things 1 per cycle, you will be able to get at least 1 instruction issued and retired per cycle. So one of the important things as well about our modern processes, the one that's often hidden from view when we see multi-core processes, is vectorization. So as I said, a vector unit will issue instructions that in order to amortize the cost of the decode of the instructions, it tries to issue an instruction on several pieces of data at once. Now, our modern scalar processors, as we think of them, right, a single Intel or AMD core, now has a vector unit, a SIMD unit, single instruction, multiple pieces of data. It does the decode once, and there's a set of pieces of data that it can use. It can issue that instruction against. So we've been doing this now for about 15 years, and certainly 10 years or more in anger, so to speak, with SSE. Okay, that's streaming SIMD extensions to the x86 instruction set. There's also on other architectures, for example, here we've got a mention of some of the Power PCs from IBM. You have Altivec, or a double Hummer or a quad Hummer on a Blue Gene Q. And these provide very small vector units, so the vector might actually be only 2 things long. And in this case, that means that the vector is simply how many pieces of data that are contiguous in memory can we issue this against. If you aren't able to take advantage of these SIMD units, you'll get worse performance. Remember I said that 64x performance, and we could divide it down, and we ended up with 4x. That 4x all comes out of these units. And that's because also these instructions are getting wider as we go on and on and on. So our latest Intel and AMD processors can issue 4 instructions against 4 pieces of data at the same time. Now, SIMD units typically require data to be contiguous in memory. Some of the latest ones are able to start to work more towards gather-scatter, where they can look around in memory and collect pieces of data together before working on them and put them back in the appropriate way. This is reinventing technology that was there 20 to 30 years ago, but where we used to have very large vector machines that could issue 256 pieces of data with 1 instruction. And those who are interested in GPUs, there's a similar form of SIMD called SIMTIB, single instruction, multiple thread. And there the data does not have to be contiguous. You can do things differently. You still issue 1 instruction against multiple pieces of data, multiple threads. They don't have to be contiguous, but for performance reasons, you still have to get them contiguous. Or not necessarily contiguous, you have to get them in a way where they're all very close together. So our hardware, our multi-core processors. Multi-core processors would have multiple cores per physical socket. These cores are independent. So unlike when people talk about some of the GPU cores, and they would refer to them as saying 500 core GPU or whatever, those cores aren't in the same way because they have to work together. Say 32 of these cores have to have one instruction issued against them. On the multi-core processors that we're more familiar with, they're all totally independent. They really are just like processors of old, shoved onto the same processor die, processor socket. They share some resources. They have to compete for memory bandwidth, maybe the highest level of cache. On some of the processors that we have, such as these AMD Interlagos processors, 2 cores even compete for floating point units. Now, we typically talk about processor cores and then a socket with all those cores on it. In the case of some of our processors, the socket itself is effectively 2 multi-core processors glued together. Not physically glued, that probably would be a very good medium. And we have to be aware of this when we actually come to program. So the 2 processors, the 2 most modern ones, the ones that we're looking at, the one is the Sandy Bridge from the machine I just mentioned was arriving, just being put together now. This has 8 physical cores. An Interlagos processor, the one that is our largest machine at the moment, our current flagship machine, that has 16 cores, but it's effectively 2 multi-core processors in itself. So when we build this up onto a larger node, then we get 32 cores, but in a very strange configuration. So multi-core processors, if we begin with multi-core processors, then we move on to the multi-socket nodes shortly. So processors have become multi-core. You'll have realized this, of course. How many people, is there anybody in the room who doesn't have at least dual core on their laptop, for example? Actually, if there is, I won't ask because it might be embarrassing. My choice when I was just buying, well, I wasn't buying, CSCS was buying, this laptop that I have here was dual core or quad core. So, well, I went for dual core because it's a nice, pretty machine and I don't necessarily need the others. But when we come to server processors, then we're looking at typically 8 cores is the minimum pretty much that you get these days. So an IBM Power 7 processor, big beast, 8 cores. Most of these things will be 8 cores. The largest machine in the world as of about a year and a half ago had 8 core processors. The largest as of 6 months ago had 16 core processors. The largest at the moment has GPUs. AMD Manu-core processors, that was one of those that were mentioned where you actually, on that multi-core processor, you glue 2 others together. That was 2 times 6. The Interlagos has 2 times 8. So a processor become multi-core is actually even more complicated than that sometimes because some processors become multi-threaded. So the Power 7 that we mentioned with 8 cores, that supports up to 4 hardware threads. The Nehalem, the Sandy Bridge particularly has 2 hardware threads. AMD Manu-core don't, but they have some extra features about sharing floating point units. The Blue Gene Q has 4 hardware threads. The Fujitsu also doesn't. Now, what does all this hardware thread stuff mean? Well, there's no physically new resources typically for hardware threads, but it may be on some architectures, such as the Blue Gene Q, or such as the Xeon Phi that we'll hear about on Wednesday. If you don't use the hardware threads, if you don't start to overload your cores, you can't get the maximum performance. So this is just like if we don't use the vector unit, just as if we don't use all the cores. If we don't start to use some of the hardware threads, then we actually lose out as well. The hardware threads are there because typically, or the reason they were originally there was just that, as I said, there were certain capabilities in processors to try and get on with some work, even if the processor would normally stall. Well, if you've got a completely separate execution line somewhere, a different MPI processor, a different OpenMP thread that doesn't even rely on these instructions at all, there's a chance it might be able to do some useful work even if the other one's stalled. Now, why was this important if we've got this big depth of 40 or 60 extra instructions? One of the reasons is because our memory latencies have never been able to keep up in recent years with our clock speed increases. Now, we've stopped with clock speed increases, but the memory latencies haven't changed at all. So if memory latency, really loading something from memory, takes 200 clock cycles or more, clearly even our 40 or 60 instructions out of order isn't going to help us. So by having multiple different things where they're waiting on memory, if one of them really does stall, the other one might still be able to get on with something. It's better at hiding memory latency. They're not the same as operating system threads. Each hardware thread could be a completely separate process rather than a thread. So the threading that we look at, threading is now a very overused word. Threading is talked about in the context of GPUs. It's talked about in terms of things such as OpenMP, and it's also talked about on hardware level. Now, so that's our multi-threading, but many of these nodes have become multi-core, multi-socket. So first of all, get the ones out of the way that haven't been. So Blue Gene Q nodes have one multi-core processor. So that's physically just one processor. There's some levels of cache, and then all those cores see one view of memory. And this is something that will be important later on when we look at NUMA and Affinity on Wednesday. The Fujitsu K machine, that's again one multi-core processor. And if we have some nodes that have GPUs on them, you may just have one multi-core processor in the GPU. Now, if we take particularly the top two, the Blue Gene Q and the Fujitsu K, who has access to that in the room? Either of those. So that's why it's not really that important to us to concentrate on a single multi-core processor. We instead have to look at multi-socket nodes where there are multiple multi-core processors together. Because there was not a single hand for the others, even though I know there is somebody over there who does have access to a Blue Gene Q or did have. The Cray XE6 nodes, this is one of the three machines that we're going to be using in the practical. For example, that's multi-core, multi-socket, and multi-die. So there are 4 nodes there. So a multi-socket node consists of a number of multi-core processors and a global memory that they can all access. From an application point of view, when you're actually just sitting there with the operating system, if you say, I want some memory, you don't ask, can I have it from here or there? We'll give some instructions on how you can launch your job to try and make sure that you get memory that's local, but you see it as one just big block of memory. That's not actually a very good view because there's local and there's remote memory. So for a single multi-core node, those ones that we don't have access to, this isn't really a problem. But for multi-core and multi-socket nodes, we have some more complications. So just have a look at a couple of the nodes that we have at the moment that we can see. If you look at physically 2 of the machines that we'll be looking at, one is a Sandy Bridge cluster, and one is a Cray XE6 with Interlagos processors. We talk about it as being 2 Interlagos processors, and on the right-hand side. On the left-hand side, 2 Sandy Bridge processors. You can see it as at one level, particularly on the right-hand side, the way that the largest Cray XE6 in the world, this is the one at NCSA in Illinois, they look at it as being this similar. The 2 sockets are connected by some sort of fabric. In this case, it's QPI. And over here, it would be hypertransport. And they look very similar. But actually, as I said before, the Interlagos is 2 dies on one socket. The compute units are actually multi-cores in themselves. The one on the left, the Sandy Bridge, it has a physical core with hyperthreading. This one is different. This one has 2 separate cores. So when we strip away what we see from the outside, when we physically look at a board with a couple of these sockets on, is that, I'm actually talking about them the wrong way around. They're so similar, I actually got the, which one was the Sandy Bridge and which one was the Interlagos wrong. When we actually strip away the outside, that socket becomes 2 dies. And within the dies, they themselves, it suddenly becomes apparent, are connected by the same weaker connection than the cores. And that is, it's also connected by hypertransport. That makes a big difference, because now we can't say that we want to have all of these cores working together on the same view of memory, because if this one wants to access the memory over here, it has to jump first to get access to it. The second thing is that those cores, what we look at as one core, and it can grab all the floating point unit, but it's actually also got this dual core effect up at the top. So we're going to look at multi-core effects later, and that's why we're going to concentrate on single core performance just today, just to begin with, just having a quick look at some cache effects, but also about vectorization in particular, because these things can get very, very complicated, and therefore they do need a day or two of work to understand. But they are the predominant processor technologies that you will come across in your day-to-day work. And so it's important that we do look at all the effects and what these mean. And for single core performance, therefore, we assume that we're always getting local memory, and we don't have to worry about any strange effects of running too far away. So just to confirm that you've really got access to these machines that we said earlier, we'll actually just begin with, we'll have a little exercise as we look now. On each of those machines, I'd like you to do the following. This also just is one of those things so we can make sure that the salloc and all the other instructions work and you're happy with them. So on each of those machines, get a salloc session as it's written down on the instructions, and then using the way that we launch jobs on the compute node using srun or apprun, just run the command numactl ---- hardware. And then afterwards, you release the salloc sessions back into the pool so that then somebody else can use it afterwards. This is what you would see if you, on Ayla, run this command. And it will tell you about the different node, about how many different nodes it sees. Node being a set of multicores attached to one memory. Ayla is an old machine. It's now 4 years old. And so there was quad-core processors. So it tells you about the processors that you see. It tells you how much memory is there. And then it tells you about how far away it is between each of these different NUMA nodes. In the case of these machines, we want you to use these srun or apprun commands. Otherwise, you're on the login node, just sitting where you were. If you use these commands, then you will actually be able to launch your jobs. And then each one should split the memory in between two. So what you're actually seeing there is, so I can describe that even if we've just got the one machine. Two nodes. In this case, it's physically two sockets, two multi-core processors. Each is attached to its own memory. So numactl, NUMA, I think, Ben, you'll be talking about NUMA effects on Wednesday, correct? Yeah. So you'll understand a bit more about what NUMA means then, but effectively it's saying this is two nodes, each with multiple cores and processors, memory attached, and then some way of talking across some barrier. In this case, we'd have 4 of these. If you got onto Rosa, unfortunately, you can't. You would see also 4 of these. What you see on Pilatus as well is it goes 0, 1, 2, 3, 4, 5, 6, 7, and then it starts again at 16. The second set of those, the 8 cores, are not real cores. Remember I mentioned about the hyper-threading? Well, those are then reflections of cores 0, 1, 2, 3, 4, 5, 6, 7 again, but with an extra little slot for the thread. So there are actually only 16 real cores on that node. So what it does is it gives out, it says there are 8 on the first and then 8 on here. And then if you needed a 17th core, it would start overloading those again with the hyperthreads. That's why it's given you so many, what looks like 16 cores per node. And so, since we can't see the other machines, and to give ourselves plenty of time to make sure we're ready for the next exercise, it's probably a good time now to break for coffee, because I can see that the croissants are out there.